Hi guys, here we are again. So today we are going to see a little bit of BME, Basic Mechanical Engineering, and we are going to study a bit. Okay, this is a video just to explain what is process and just to explain to give a quick review on the processes of thermodynamic. Okay, for property of gases. Okay, because there are very five five okay, there are five processes that are really important to know. So yeah, we are going to start with starting these first processes. Okay, first of all, right here the processes that we are going to study in property of gases. This is very important for solving the exercises and also to understand the processes on any engine, IC engine, and also to calculate the numericals. It is also linked to numericals of property of gases or property of gases and calculus on also on IC engines also. Okay, let us start. See, first we have okay, we have five processes. I can say like this one. I will write here 1, 2, 3, 4, and 5 processes. So here in this video we will try to summarize some of them. Okay, see, first processes that we are going to start studying, it is about this is the um, isobaric. Okay, isobaric process. Okay, isobaric process. The term isobaric, okay, iso. What does it mean, iso? Iso, it's the same. Okay, iso means the same. This is a Greek word. Okay, iso, same. Baric, it is related to the pressure. Okay, baric, it's like what is the unit of pressure? Okay, bar. Bar is also a unit of pressure, even though it's not a how can I say, a SI unit of pressure, but bar is a unit of pressure. So whenever you see baric, bar, it is all related to pressure. So this is the process in which pressure is constant. Okay, in this process, pressure is constant. So from PVT, okay, relation, when pressure is constant, what we will get? Volume, okay, volume will vary, okay, will be directly proportional to the temperature. So it means that we will have this one V1. Suppose we have two states, V1 upon T1 will be equal to V2 upon T2. Okay, in a nutshell. Okay, this is this. Hope you can all see. Okay, you can all see. Hope you are all see. Okay, in a nutshell, this is this. Okay, nice. The second process that is very common, this is isochoric. Okay, isochoric pressure process. So for isochoric process, okay, here the volume is constant. So here we will see what will be the the behavior of a gas, of a perfect gas, when the volume is constant. When the volume is constant, we know that the temperature will vary, okay, in the same rate of pressure. I mean, if I keep the constant volume of a perfect gas, the temperature will be directly proportional to its pressure. What does it mean? If I increase temperature, pressure will increase. Okay, then the expression, the variation, or the expression, PVT expression for this process, it is T1 upon P1 is equal to T2 upon P2. We will vary this formula according to Mendeleev-Clapeyron equation. Okay, we will vary how we are getting this one. And also, and the third process that we usually know, okay, in property of gases, it is the process, okay, the iso isothermal process. Okay, in this isothermal process, we have to understand this is the process at which the temperature is constant. So it's like iso, it is same. So thermal, it's linked directly to what we used to call thermal. Thermal is nothing more or less than temperature. Okay, so same temperature. Okay, same heat transfer, same. So here, when temperature is constant, what we say that the pressure of a gas, of the perfect gas, vary inversely proportional to its volume. It means that when the when the temperature is constant, if I increase the pressure of a certain perfect gas, the volume will decrease. And if I decrease the pressure, the volume will increase. Okay? So the relation PVT of this process, it is P1 for first state, P1 V1 is equal to P2 V2. Okay, that's the point. Then we have then we have adiabatic process. Okay, we will speak about all these process in detail. Okay, adiabatic process. In adiabatic process, it is that process in which there is no heat transfer. So for adiabatic process, heat transfer is equal to 0. So heat transfer is equal to 0, and the relation between PVT, okay, we can get a lot of this relation. So I will not write down all the relation. We will just derive all the expressions for adiabatic process, and also for the last one, that is polytropic process. Okay, polytropic process. Yeah, these two I will explain in detail, okay, but in the next section. Today we are going to start from 1, 2, 3 for isobaric, isothermal, and isobaric, isochoric, and isothermal process. What is this? What is the work done in isobaric process? What is the enthalpy? What is the internal energy? What is the relation PVT, and so on. Okay, we are going to find for this one, this, and this. And in the next section, in the next video, we are going to explain about adiabatic process and polytropic process also. And we will end, in the end of all of this explanation, we will end with a graphic of adiabatic, with the PV diagram for the whole process. Okay, for all the processes in here. Okay, nice. Now let's go. Let's move. So we will start with isobaric process, then isochoric process, then isothermal process. Okay. Guys, if you understand this very well, it will be very easy to you to understand all these numericals about property of gases and things like that. This will be easy to you to understand them. Okay, so isobaric process. As I said, isobaric process is the process at which pressure is constant. So pressure is constant when pressure is constant. That's the point. In this one, we are going to calculate what is the relation PV, okay, PVT relation, okay, PVT relation. For this one, what will be the work done, okay, for isobaric process. 3, what will be the heat transfer, okay, heat transfer, I will just say Q, this is heat transfer, okay, heat transfer for the process. And what will be internal energy, delta U, internal energy for this process, okay, what will it be? And also in the end we will find what will be the change in enthalpy for this process. Okay, we are going to calculate all of this in this process. Nice. Okay, just stay on. Okay, I will start for the first one, what is PVT relation for this process in the beginning. So what is PVT relation? So PVT, it is nothing more or less than we know what is the characteristic gas equation. No, characteristic gas equation. If you are not aware, how can I say, if you are not aware about this characteristic gas equation, look at the very first videos in this program. You will see there how to derive the characteristic gas equation. So we will use that the characteristic gas equation formula, okay, MRT, to derive what is the PVT relation in isobaric process. Okay, so see, here we have a gas and PV is equal to MRT. This is the equation for gases. So PV is equal to MRT. Now I will consider these guys, the same gas, it means the same mass and the same R, the same gas. It will vary according to two. We will have two states, okay, two states, and it will vary according to these two states. So it will have state 1, P1, V1 is equal to MR and T1, okay, and second state it is P2, V2, it will vary MR and T2. Now what is this? What is the relation in isobaric process? We are finding relation PVT for isobaric process. So we know that for isobaric process P1 is equal to P2 because this is constant. So what do we have to do? We have only to find P1 here and P1 in P2 here, then equalize them. So for 1, it implies for 1, P1 will be equal to MR T1 upon V1. For 2, it will be P2 equal to MR T2 upon V2. Right? SP, okay, hope you can all see. SP1 is equal to P2. So MR T1 upon V1 will be equal to MR T2 upon V2. So from here you can just simplify this MR, okay, because I said this is the same gas, okay, the same gas in different state, okay. So this and this is out, so what we will end, so this is the relation. When pressure is constant, T1 upon V1 is equal to T2 upon V2. Okay, this is the relation of PVT. This is PVT relation on isobaric, okay, isobaric process. PVT relation on isobaric process. This one is the relation. Okay, now we are going to calculate what is the work done. Okay, work done for the same process. Okay, now work done for isobaric process. Okay, what is work done for the isobaric process? See, first we have to draw. Okay, we will draw the PV diagram, this one, and then we know isobaric process. So for isobaric process, it means the pressure is constant. So I will draw here constant pressure. It will be like this. It means that P1 is equal to P2. I will call this 1 and 2. Here I have only one pressure. Okay, here P1 is equal to P2, and here I have V1, here I have V2. So what will be the work done, okay, of this guy? The work done for this guy will be what? Will be this area, okay, and this area can be calculated, okay, can be calculated directly by what? Will be calculated by the limit, by the integration of this one. So I want to calculate this one. This one can be calculated by integration. So This will be the higher limit, upper limit, and lower limit, V1. Okay, and this will be what? Constant pressure. We have constant pressure, and volume is deriving, so it will be P and V. P D P, sorry, P D D V, sorry, P D D V. Okay, so at constant pressure, this guy will be directly equal to constant pressure, and here, if we calculate this integration, what we are going to have? We are going to have V to the power 0 plus 1 upon 0 plus 1. Okay, it is V2. It's varying from V1 to V2. So this will be P. Then what you get here? V only. So this is V from V2 and V1. Okay, it will be P, and here you get for the first interval, then the second limit minus V1. Okay, so the work done for isobaric process will be P. Okay, I can write P delta V or P dV. Okay, it's up on you. This will be V minus V1. Okay, this is the same as P delta V. So, okay, now we have derived the work done for isobaric process. Nice. So this is the work done for isobaric process. Now what we are going to find? Now we are going to find what is delta U. Delta U is internal energy. Okay, internal energy. This is the energy that will result okay, when we got interaction in the molecule, on the internal molecule of a certain substance. Okay, and it is always a function of time according to Joule's law. A function of time always. Okay, so sorry, not time, temperature is a function of temperature only. It means that the internal energy do not depend of anything. Okay, just depend on the temperature. If the temperature varies, it means that we have variation in internal energy. If the temperature varies, so we have delta U, that is a change in internal energy. But if temperature do not derive, so there is no change in internal energy, this will be 0. So for this case, only pressure is varying, so it means that we have change in internal energy, because here time is varying. Oh, temperature is varying. Sorry, because of this time, it is temperature. So then delta U will be equal to M CV delta T always. Okay, then here there will be no change. Okay, delta Q is only a function of time. So as time is varying, so there is change in enthalpy, there is change in internal energy, and that will be all. Here CV, okay, CV is the specific heat, okay, specific heat at constant volume. That's why you see CV here. Okay, just like this. So what about the heat transfer? Now Q, what will be our Q? Okay, Q, that is the heat transfer for isobaric process. Let me call here Q is heat transfer. Okay, for isobaric process. So Q, as we know from the first law of thermodynamics, this is I will call this one, this is Q will be given as by the first law of thermodynamics. Okay, Q will be equal to W, work done, plus change in enthalpy, change in internal energy. Okay, so we know what is work done for isobaric process, and we know what is change in internal energy for isobaric process. So Q here will be P, okay, delta V. Some people just will call delta U, but it's okay. P delta V plus M CV delta T. So this is heat transfer for isobaric process, just like this. Okay. Now what will be the what will be now what will be enthalpy? Okay. What will be our enthalpy for isobaric process? Enthalpy, as we know, change in enthalpy. Okay. Enthalpy, it is nothing more or less than enthalpy, just enthalpy H. It is the summation, okay, summation of the work done, okay. It's the summation of PV, okay, PV plus U, okay. U is internal energy, okay. At one state it will be P1, V1, and so on, U1. But here we will analyze change enthalpy. Change enthalpy, why? Because we're analyzing for isobaric process, not for only one step. Okay, for process must have more than one state. So for a process, it will hold two state. If it has two state, then I will have here P, and here it will be delta V, okay, plus delta U, okay, plus delta U. This one is your isothermal, this one is your isobaric enthalpy, change enthalpy for isobaric process, okay. So then you can from here calculate directly what is your, so we know that PV, it is mRT, okay. And here we know that delta U is mCV delta T. So change in enthalpy will be what? See, what is R? We know that R, okay, R that is gas, characteristic gas constant, is given as Cp minus Cv. This notation is already known, okay. Yeah, this is already known, and it can be calculated, okay. It can be calculated also in a certain time. I will just show you, okay. Now just take it one. R is Cp minus Cv. So R is Cp minus Cv. If you just put this one here, so delta H, that is your enthalpy, okay. Hope you can all see. That is your enthalpy, will be equal to m Cp minus Cv delta T, okay, mRT. Here, as we have two state, it will be delta T. Sorry, it will be delta T. We have two state 1 and 2, so it will be T1 or T2 minus T1 for this guy. So mCv delta T plus mCv delta T. Okay, now we just can extend, okay. Delta H will be mCp delta T minus mCv delta T plus mCv delta T. Okay, so here we can see that these two can be cancelled out, this and this. So then I will end that change in enthalpy will be equal to what? Will be equal only to mCp delta T. Okay. Thank you very much, and I hope it can be helpful for you. So for isobaric process, we have derived all that we can know. Okay, thank you. This is for isobaric process.